The two topics for this lecture comes from chapter 13, linear or line of balance schedules, and project administration case studies. The objectives for this lecture are to describe a line of balance type of schedule. We'll discuss where they're used and primarily how to produce one. And in a separate video, we'll go over one additional example. Within this type of schedule, there's things called buffers, which relate to time and or distance, which is the space in between actual construction or manufacturing activities. That's all related to line of balance schedules. Then at the second half, we'll discover project administration case studies. You'll see when we get there that I took a sort of unique approach and talked about poor administration of projects and how that resulted in issues. So these types of schedules, obviously they're titled linear schedules. They're sometimes referred to line of balance schedules, and they generally have the roots in the manufacturing industry, primarily because they're real repetitive in nature. The project's each individual activity continues to happen throughout the project. This is a completely unique schedule unto itself. It's not related to the CPM type schedules or network schedules that we've been doing in this class. They look completely different. They have similar steps to set up. One primary thing to note is that these types of projects are horizontal in nature rather than vertical projects. What I mean by that is highways, pipelines, and railroads. Notice that those go along the ground rather than starting from the ground and going upwards. So here are the primary steps to create this. You'll see, like I just said, they are similar to creating a CPM or network-based schedule, but there's little differences in them, obviously, because they're different types of schedules. The first one, identifying the activities, that's exactly the same. You need to figure out what activities need to occur in your schedule, and you could just do this by creating a list again, just writing them all out. You will probably write them all out in chronological order already, but possibly not. You might remember some towards the end. But that's the first thing, is figure out what's going to happen in the schedule. The second thing is to estimate the activity production rate. This is very similar to the CPM type schedule, where you estimate and determine the duration of each individual activity, but instead we're determining the rate of each individual activity. In a conventional lecture, when I teach this, I usually ask for students to give out examples of rates. But in this instance, other examples of rates are anything over time, such as miles per hour, how fast you go in your car, gallons per minute, like a fluid flow rate. Those are just some general examples. In this instance, we're going to be talking about for the amount of distance covered per time, because it's a horizontal type of construction or manufacturing schedule. The third thing to do is develop the sequence. So this is very similar to the previous schedules. You have to put them in their proper order, predecessors and successors alike. Then next, the fourth thing is to create a velocity diagram for the first activity. So this is completely new. What is a velocity diagram? Well, first I usually ask, what is velocity? Well, I just gave one in my previous example of a rate. It is basically a speed, so miles per hour, some sort of distance per time. Miles is kind of long for these types of schedules, so we'll probably be working in feet, hundreds of feet, meters per hour or day, something like that. And the diagram portion is just an XY graph that we've traditionally have seen in this class before, or probably in other classes that you have plotted. That step 5 is add the velocity diagram for each individual activity. So we're just going to add the activities to this plot. Then, similar to other activities, other schedules, you refine the schedule. You created it, you looked at it, you've done the math, you looked at everything over. So the step 6 is to look for any conflicts and or buffers. So buffers is a unique thing to look out for in this topic. We'll go over that when we start going over the example. So here's the first example we're going to look at. It's an example for 5,000 feet of pipeline. Think like a gas pipeline, water pipeline, anything like that that just covers 5,000 feet distance. I've already done step 1 in this example. I've told you the activities. The first activity is survey and layout. That's one activity together. Clear and grub, that's the second activity together. Trench, pipe, and backfill. So just these activities, and that's it. They're already in chronological order for this example. So step 1 is done. Then we need to figure out the production activity. So here they are relisted in this table in the order: survey and layout, clear grub, trench, lay pipe, backfill. I've already given you the production rate. And again, just like with the CPM type schedules, if you don't know this, you can refer back to the other lecture to figure these things out. You could use a manual. You could talk to existing people who have done this before and estimate these numbers. So I've given to you these already: 500 feet per day, 400, 200, 300, and 250 respectively. Now, what wasn't listed in the previous slide as far as what to do is to then determine just the duration. We could do this by just simple math. We know it's 5,000 feet. We know how much it's going to take per day, so I could just divide 500 into 5,000 and figure out that survey and layout is going to take 10 days. And 400 into 500, then rounded, is 13 days. So we could actually get a duration in days for this individual activities. And you'll see that this will help us immensely later on. So I would possibly maybe go back in your notes, add right here, estimate activity production rate, and also determine the individual duration. Although it's not required, I just recommend it because it helps a lot. And as I noted here, and I said previously, just partial days are just rounded up to the next full day. So where we're at in the process, we've done these first 3. Now we need to create the velocity diagram. So here's a velocity diagram with the first activity actually added. You'll see, as I previously said, it is just a plot. On the x-axis is duration in days, starting at 0. Each little increment is 1, so 1, 2, 3, 4, 5. I know the numbers are slightly off with the major dark bolded lines. And then on the y-axis is the distance, and this is in thousands of feet. And you notice our schedule only goes up to 5,000 feet because that's the ultimate distance of our project. And so now these are the major tick marks are in thousands, and it's all ultimately in feet. Now we just plot the first activity starting at the end of day 0, which is here, and we know it takes 10 days to complete based off of our math 2 slides previous. So if it takes 10 days, it starts on day 0, then it is just a straight line connecting 0 to 10. And the slope of the line refers to the production rate from here, 500 feet per day. So that's all we basically do for this entire type of schedule, is add lines to this graph. And the refining the last bit of the part is to ensure that none of the lines actually intersect with each other. Because remember, this refers to actual location of people and or equipment at a specific location and time. What I mean by that is at day 5, I could look at the schedule and extract information by going up here and hitting the line, and I will see that I'm halfway between, about 2,500 feet into the project. Then there will be other lines added to this plot that go along here, and then you could do the same thing and extract information. But if lines ever intersect, well, then that's a problem, because you actually haven't finished survey and layout before you're adding another activity to it, and you might overtake those activities. And all these activities in the schedule need to happen sequentially, so then therefore none of the lines can intersect. So let's continue along and we'll see more about that. It is possible for these types of schedules to have a kink in their line that would mean that their production rate would not be constant, obviously. In the example, we're not going to have that, but it's good to talk about and know that that's a possibility. That survey and layout or any of these other activities could have a kink. The production rate could slow down, but it could also go faster for some reason. But there could actually be instances in real life that this could happen. For survey and layout, there could be trees or grub or lines or fencing lines or things in the way that is just slowing down your production rate. And so notice in general that the more line the slope of the line that's more horizontal, the production rate is slowed, versus if the line is more vertical, then the production rate is faster. And so if the production rate is at this 500 feet per day, then it changes here. It's slowed down. It's less than 500 feet, but then it kicks back up. So something happened in between 2,000 and 300 feet. There could be something in the way. So this is something that could theoretically happen with any of the activities on these types of schedules. So it's just something to note that it's possible. We'll continue on to the example and add the next one. We'll use a constant productive rate for this example. The next step is to add the next activity and continue on from there. So clear grub is the next one. We add that to the linear velocity diagram. This one has a lower productive rate, therefore we know that the velocity diagram will be less steep, like I just said in my example. So here's where the management team could start using the schedule to their advantage, or ensuring that there's enough space everywhere. The management team wants to start clear and grubs 2 days after survey and layout to make sure that these two activities will not conflict, so that their lines will not cross. In addition to that, so that there's enough space for people and equipment to do their individual activity. You could get real close to the lines on the graph, but you also want to ensure that you have enough space for safety reasons and for good quality and control reasons. So clear grub has a duration of 13 days, but we want to start it 2 days after the previous activity. So we just add that to its duration, so that would be 15. And so see, we don't start on 0. We start 2 days after it, giving our start date to end of day 2. And we know that this has a duration of 13, plus that 2 days gets our last data point at 15. So that's how we determine where clear and grub goes. Okay, then we're just going to continue along the line and add the next activities. The next one is trench. This has a production rate of 200 feet per day and therefore a duration of 25 days. This production rate for trenching is even lower than it was for clear and grub. Obviously, we're like digging a hole, like a linear hole, so it goes real slow. It's not as fast as just walking and investigating, doing the survey and layout. So this one's going to be it's going to be less steep, more horizontal than vertical. The management team decides that they want to start trenching 1 day after clear and grub starts. So I'm going to continue on to the next activity. The next one is lay pipe. This one has a duration of 17 days. This production is higher than the trenching productivity because these pieces of pipe could come up to 40-foot lengths, and so that means that the activity can go real fast. So knowing that this one goes real fast and the previous one goes real slow, this is where we could easily have an issue where they would definitely intersect. So the first one is to dig the hole. The second one is to put the pipe into the hole. And so literally these two activities in relation to each other, if there's no hole dug, the linear trench dug, then you can't put the pipe in there. So you want to ensure that the trenching is done completely before laying the pipe. So this is where you'll have to start to figure out when should lay pipe start such that they don't conflict. So this is the slide that basically describes what I was just talking about. This will quickly overrun, lay pipe will quickly overrun trench activity. The pipe obviously cannot be laid until that trench is dug. So one of the benefits of this method is to forecast these conflicts so that you know when the proper date to start all of these activities is, so that you don't overrun each other and have these conflicts. So since this has a steeper slope, then what we do is we look at the finish date instead of like at the start date, what we were doing before, when we know we have two activities where the first is slower and the second is faster. Then we decide how many days after trenching the first activity is finished, so that lay pipe activity should also finish. Then we go backwards to determine when the start date is. So in this case, the management team decides that they want lay pipe 2 days after trenching is finished. Notice it says finished instead of start, as with the previous examples. So what they're actually asking for is a 2-day time buffer. Remember, this is one of the objectives of the lecture, is to talk about what buffers are. This is the first appearance of one, and it's called a time buffer, since it obviously refers to time as in duration of days. And we want 2 days in between the activities. So then what we do to add these 2 activities is we draw backwards from the finish to determine the start of the pipe.